Did you know that your phone probably encrypts more data in one day than most governments handled a few decades ago? Every HTTPS website, banking app, WhatsApp message, password manager, and many cloud services rely on encryption. Encryption is why someone on the same cafe usually cannot just read your passwords. When you share the same Wi-Fi with HTTPS, they might be able to observe that you are communicating with a service, but not simply read the contents of the encrypted connection. And modern encryption is based on problems that are very easy in one direction and extraordinarily difficult to reverse. Think of multiplying numbers, for example. It's easy. However, reversing certain mathematical operations used by cryptographic systems can become computationally impractical. In essence, encryption describes the process of disguising information by converting it to a form that is unreadable by unauthorized parties. Modern encryption algorithms use what is called an encryption key to encrypt data into a secure form. And a decryption key it's used to decrypt back into its original form. When you use the same key to encrypt and decrypt data, we talk about symmetric encryption. In this case, we have a plain text that is being encrypted. Is going to get a key to create ciphertext, and then that same key will decrypt the information back into the plain text. This is using Wi-Fi, password managers, and disk encryption. On the other hand, we have asymmetric encryption. Asymmetric encryption is a bit different because it uses one public key and one private key. Don't worry, it's actually easier than it seems. A different key is used to encrypt and decrypt the data. The encryption key can be actually made public, while the decryption key is kept secret. A website server can give away their public key, allowing any user to encrypt their data sent to them in a way that only the web server can understand. So think of this example. Imagine you're giving everybody a key to your house that locks the room or locks the actual door, outside front door. However, nobody else except you can actually open it back. This is perfect because that means you can share a key to the public internet. They can talk to you or talk to your web server in a secure form. But only you can unlock that information. And that's what asymmetric encryption allows secure browsing on the internet. And this is a sentence that I really like that visualizes this concept. Anyone can lock a box, but only the recipient of the secret information can open it. Hash algorithms can be thought as an encryption algorithm whose output, also known as hash value, cannot be decrypted. For example, if I enter ABC, that ABC, when it's gonna be hashed, it must generate an output. The next time I enter ABC and I use the same hashing algorithm, it should generate exactly the same output. As a general rule of thumb, every equal input with the same hashing algorithm and nothing else, no other variable changing, means that I should be able to get the same hash value. If for some reason I have two different inputs instead of ABC, and then I also have ABD inside my input, and I get the same hash value or the same hash output, that means there is a collision, also known as hash collision. You can use hashing algorithms to determine whether the same input has been entered twice, or whether an input has unexpectedly changed without the application having to store the input. The power of hash algorithms is that they allow you to detect changes in data without having to store the data itself. Let's look at two examples: password and sub-resource integrity. A good practice when you're using passwords is that every time you create a new password or a new user, you hash this web server should hash that password and store the hash. Additionally, with other security requirements, of course. Imagine the web service actually storing the hash. Once you log in again and you enter your older password, what the web service should be doing is to check the stored hash against the hashed password that you just entered. They compare it, and if they match, actually you can enter. Otherwise, it will be refused, right? It will be denied. Bear in mind that here on passwords, the actual comparison is on hash out values. You are not comparing the raw string or the raw password value. This is not a good practice and should be avoided. On the other hand, you have sub-resource integrity. This is more when you deploy websites with JavaScript resources. Whenever you have sensitive files, what you could do is to check whether a file is actually matching to what you expect it to be. And you can use hash algorithms to do that. In this case, imagine you have a JavaScript file, you enter the whole original file into a hashing algorithm, and it returns a hash output. That hash output is you can put it in your HTML from your website as integrity. This integrity code or output, it will be the one that it's for you, the reference as the true value of what the file should be. If for some reason there is any suspicious activity or some unexpected changes into that JavaScript file, the hash output when loading it will be different than what you have in your HTML attribute of identifier. And if that doesn't match, that means that the original JavaScript file has been modified unexpectedly, and therefore it will not load. These are ways to check your file integrity and keep your files safe, or at least understand what's happening. This is also used, these hash algorithms, I have also used them during my work when I was doing data engineering. For example, if you want to check when a data value has changed or checking data integrity, that could be maybe you want to check a row that you expect it to be static and not change because it was historical data. And then suddenly you get a new hash that doesn't match with the original one. You know that there has been at least one change in that row input. So thank you very much. And if you have any questions, happy to answer you in the comments.